today we're going to learn lesson 9, rational functions, part 2. Learning goals for today. After this lesson, you will be able to sketch the graph of the reciprocal of a quadratic function. Analyze the key features of the reciprocal of a quadratic function and determine a possible equation given the graph of the reciprocal of a quadratic function. So we'll be learning the graph of reciprocal of a quadratic function. So there are 3 cases. First case is when the quadratic function has 2 different zeros. Second is when the quadratic function has only 1 zero. And last case is when the quadratic function has no zero. So let's have a look at these cases one by one. Okay, first of all, let's have a look at the introduction of the reciprocal of a quadratic function. The reciprocal of a quadratic function has the form f(x) equals 1 over ax squared plus bx plus c, where a is not 0. In this lesson, we'll try to sketch the graph of f(x), assuming a is greater than 0. Because when a is less than 0, the logic to sketch the graph is basically the same, right? Except that the direction may be different. All right, so first of all, let's have a look at the first type of cases where the quadratic function has 2 different zeros. Okay, let's use the example to illustrate the methods we sketch the graph. Okay, so first of all, let's have a look at the function here. f(x) equals 1 over x minus 1 squared minus 4. All right, so basically it is obvious that this function here is a quadratic function, right? And it has 2 zeros, which are x equals minus 1 or x equals 3, right? These are the 2 zeros. So in order to sketch the reciprocal of the graph of this quadratic function here, first step, we need to simplify this function if needed. Okay, so let's have a look at this function. No need to simplify further, right? And then sketch the graph of the denominator, labeling the vertex line of a symmetry x and y intercepts, if any, to help analyze the behavior of its reciprocal. Since the denominator cannot be 0, the 2 zeros of the quadratic, minus 1, 0, and 3, 0, divides the region into 3 parts. So first of all, that means, first of all, we need to draw the sketch of the quadratic function, right? So quadratic function has a shape like this or this, because here the leading coefficient is positive. So for the particular problem here, it has a shape like this, opening up, right? And the 2 zeros, as you can see here, are minus 1 and 3, right? Okay, so also because the quadratic function is in the denominator position, so it cannot be minus 1 or 3, right? Otherwise, the denominator will be 3. So the 2 zeros, minus 1, 3 here, divides the region into 3 parts. This is the first part, and second part, and then third part, right? There are 3 regions. Okay, step 2. Let U represent the quadratic function in the denominator. And then we know that f(x) can be rewritten as 1 over u, right? And then we analyze the end behaviors of f(x) in the 3 intervals specified in step 1. So first of all, let's have a look at the interval from -infinity to the first 0, which is x equals minus 1, right? That means this part here. Okay, in this part, when x approaches negative infinity. Apparently, if you consider this function here, when x approaches negative infinity, u approaches positive infinity, right? And then we need to consider the function here, fx equals 1 over u, which has a sketch like this, right? We have already studied this. This f, u, this is u. Right? All right, so that means when u approaches positive infinity, fx approaches 0 from the positive side, right? And also using the same method, we can analyze that when x approaches -1 from the negative side like this, u approaches 0 from the positive side, right? So when u approaches 0 from the positive side, fx, sorry, this is fx approaches positive infinity, right? So that means the reciprocal of the quadratic function in the interval negative infinity to -1, we will have a shape like this, right? As x increases, u decreases, and as u decreases, fx increases. So in a summary, as x increases, fx increases, right? So it will have a shape like this. This is a increasing interval. Understand? Any questions? All right, so let's have a look at the other branch. For x is greater than 3, this means the interval here, right? When x approaches positive infinity, the denominator here approaches positive infinity, right? And when the denominator approaches positive infinity, the whole function fx should approaches 0 from the positive side, right? Okay, so that means when x approaches positive infinity, fx should approaches 0 from the positive side. So it has a shape like this, right? And on the other hand, when x approaches positive 3 from the positive side, the denominator approaches 0 from the positive side, right? And when the denominator approaches 0 from the positive side, as you can see here in this graph, fx should approach positive infinity, right? So here, this function will have a pattern like this. And as you can see here, as x increases, u also increases, where fx decreases, right? So that means for x greater than 3, as x increases, fx decreases. So this is a decreasing interval. Understand? And x and the horizontal asymptote is y equals 0. And there are two vertical asymptotes. One of them is on the left branch, which is x equals -1. And the other one is on the right branch, which is x equals 3, right? Okay, so now let's have a look at the branch in the middle. That means when x is greater than -1 and less than 3. So in this interval, the axis of symmetry divides this interval into two parts. First of all, for x greater than -1 and less than 3. Less than 1, sorry. That means this interval here. When x approaches -1 from the positive side, that means this direction. U approaches 0 from the negative side, right? And fx approaches -infinity. When u approaches 1 here, actually x can be 1, right? When x equals 1, apparently u equals -4, and fx equals -1/4, which is here, right? And in this interval, as x increases, the denominator u decreases, and the whole function fx increases. So x greater than -1, less than 1 is an increasing interval. It comes all the way from -infinity to the -1/4 here, right? Okay, let's have a look at the other branch. The other branch in the middle is from 1 to 3, right? When x approaches 3 from the negative side, which means this direction, right? U approaches 0 from the negative side, and fx at the same time approaches -infinity. Understand? And when x equals 1, we have already discussed this, right? When x equals 1, u is -4, and fx is -1/4. And in this interval, as x increases, the denominator u also increases, where fx decreases, right? So in this interval, as x increases, fx decreases. So it's a decreasing interval, right? So by having a look at the two branches in the middle, we can conclude that this point here is actually the local maximum point, right? Which corresponds to the vertex here, right? So that means the vertex 1 -4 of the denominator corresponds to a local maximum 1 -1/4 of fx. Understand? Okay, so basically the reciprocal of the quadratic function will have a pattern like this. It has 3 branches. One is here, one is here, and one is here, right? For a quadratic function with 2 zeros, its reciprocal have a pattern like this. Okay, next step, calculate the y-intercept of fx. So in order to calculate this y-intercept, we can just let x be 0, right? If x is 0, we can easily calculate fx is -1/3, which is here, right? So usually we'll need to label this point on the graph. Okay, then label the graph with y-intercept, local optimum is here. Asymptotes, 2 asymptotes, one of them is x equals -1, the other one is x equals 3. And any key features of the graph of fx. Last step, remove any helping graphs if applicable. So usually we'll need to remove all the auxiliary lines if we don't need them. All right. So basically, the graph shown in the blue curve is the sketch of the reciprocal of the quadratic function here. Understand? Any questions? No? All right. If you don't have any questions, let's do a practice. Sketch graph of the function fx equals the reciprocal of -x⁻²+ 4. State its domain range x and y intercepts, asymptotes, axis of symmetry and behavior, local optimum, global optimum, increasing interval, decreasing interval, if any. Okay, I'll give you 5 minutes to complete this practice. All right, have you finished? Okay, let's have a look at how we can sketch the graph of the function fx. Okay, so first of all, we need to study the graph of the denominator first, right? Okay, for the denominator here, apparently this is a quadratic function with 2 zeros, right? One of the 0 is x equals -2. The other 0 is x equals 2, right? Okay, so let's mark these 2 zeros here, -2 and 2, right? Okay, so because it's in the position of a denominator, so x cannot be any of the zeros, right? So we have 2 vertical asymptotes here. So first of all, the leading coefficient is negative, so this function is opening up and crosses these 2 points. Right? This is a sketch of minus x squared plus 4. All right, next let's have a look at the reciprocal of this function. So first of all, let's consider the interval from -∞ to -2. So when x approaches -∞, you can see that minus x squared plus 4 should also approaches -∞, right? And then we consider its reciprocal. When you need to consider its reciprocal, you need to consider this function here, right? This is x 1 over u, right? When the denominator approaches -∞, that means from this side, right? The reciprocal function should approaches 0 from the negative side, right? Okay, so basically this means when x approaches -∞, the reciprocal approaches 0 from the negative side, right? So it will have a shape like this. And also we need to check when x approaches -2 from the negative side. When x approaches -2 from the negative side, that means minus x squared plus 4 should approaches 0 from the positive side, right? Or from the negative side, right? And when minus x squared plus 4 approaches 0 from the negative side, that means from this direction, right? So the reciprocal of the function should approach -∞, right? So that means when x approaches -2, fx should have a pattern like this. It approaches -∞, right? Okay, so the other side, you can use the same method to analyze, or you can just use the property of line asymmetry to directly find its branch like this, right? Okay, I'll just draw it like this. All right, and then this is actually the line of asymmetry, right? And then we consider the branch in the middle. First of all, the branch is actually, the line of symmetry is actually x equals 0, right? So first of all, let's consider the interval from -2 to 0. So first of all, when x approaches -2 from the positive side, then minus x squared plus 4 should equal 4. Should equal 0 from the positive side, right? And the reciprocal of this expression should approach this direction, right? Positive infinity. So that means when x approaches -2 from the positive side, fx should approach positive infinity. So it will have a pattern like this. And then when x approaches 0 from the negative side, minus x squared plus 4 should approach 4 from the negative side. Actually, x can be 0, right? When x equals 0, fx equals 1/4, right? So when x is 0, fx is 1/4. So this means the left branch of the middle should have a pattern like this, right? And according to line of symmetry, we have the other branch like this, right? Okay, in order to make it nicer, let's redraw this. Okay, so it will have a pattern like this. And this point here is a local minimum. Okay, so let's make a summary. First of all, domain is x can be any real number, but not either of the zeros, right? And range is negative infinity to 0, exclusive union with 1/4 to positive infinity. And axis of symmetry is x equals 0. And behavior, we have already analyzed and behavior, right? You need to analyze and behavior here, 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 and here, right? Local optimum, this is a local minimum. Global optimum, there is no global optimum, right? Increasing interval, there are two increasing intervals. One of them is 0 to 2. The other one is from 2 to positive infinity, right? Decreasing intervals, there are also two decreasing intervals. One of them is from negative infinity to -2. The other one is from -2 to 0, right? Okay, please have a look at this. Any questions? Okay, also you can check a more beautiful drawing of the graph of this function here. Okay, any questions? No? All right. If you don't have any questions, let's do another practice. Determine a possible equation for the graph shown below. Okay. I'll give you 5 minutes to think about this question. All right, have we finished? Okay, so let's have a look at what might be the possible equation. All right, so if you see a pattern like this, it's probably a reciprocal of a quadratic function, right? So first of all, we can approach this question by looking at the two roots here. So note here, there are two vertical asymptotes, right? The two vertical asymptotes corresponds to two roots of the denominator. So one of them is -5, the other one is 1, right? So that means the two roots of the two zeros of the denominator are x equals -5 and x equals 1, right? So probably this function will look like this. Fx equals 1 over x plus 5 and x minus 1, right? In this way, the two roots are -5 and 1. And probably we'll have a stretching factor a, right? Because the leading coefficient is not necessarily 1. So probably we will need to multiply a stretching factor a here. Next, we can just insert one of the points on the graph to determine the value of a, right? So note that we can use any point on the graph as long as they are clear to you, right? So probably this point is better because when x is 0, y is 2. Probably this can make our calculations much easier. So when x is 0, y is 2. This means 2 equals 1 over a multiplied by 5, then by -1, right? So a is 1 over -5 multiplied by 2, which is -1 over 10. So a is -1 over 10. Then fx equals -1 over, -10 over x plus 5, x minus 1, right? Remember that you can always verify your result by putting another point in, right? Okay, so probably we can check this point here. When x is -4, y is 2, right? Okay, so if we plug this point in here, right hand side is -10 over 1 times -5, which will give us 2, right? Which is exactly the value of y here, right? That means we probably get the right function. Okay, please have a look at the solutions here. Do you have any questions? Okay, if you don't, let's have a look at the other type of cases where the denominator, the quadratic function in the denominator only has 1, 0. So this time, let's have a look at this example. Sketch the graph of the function fx equals 1 over the difference between x and 1 to the power of 2. So apparently there is only 0, which is x equals 1 with the order of 2, right? Okay, so the method to sketch the graph of a function like this is similar to the one we have used previously, right? First of all, simplify the function if needed. Then sketch the graph of the denominator. So first of all, we sketch the graph of y equals x minus 1 to the power of 2 first, right? As you can see here, this is a quadratic function with a leading coefficient positive. So it's opening up and it its vertex is 1, 0, right? Okay. And because the quadratic is in the denominator position, it cannot be 0 for the reciprocal, right? So at the 0, x equals 1, it divides the region into two parts. We need to consider them separately, right? First region is from negative infinity to 1. The other region is from 1 to positive infinity. Okay, next, let u equals x minus 1 to the power of 2. Then fx is 1 over u, right? Then we can analyze the end behavior of fx in the two intervals specified in step 1. So first of all, let's have a look at when x is less than 1. When x is less than 1, first of all, let's have a look at when x approaches negative infinity. When x approaches negative infinity, the denominator here approaches positive infinity, right? And then the reciprocal of a positive infinity approaches 0 from the positive infinity, right? So this function will have a pattern like this. See the blue curve here. And when x approaches 1 from the negative side, the denominator here should approaches 0 from the positive side, right? And fx approaches positive infinity. So it will have a pattern like this, right? And also note that in this interval, as x increases, the denominator decreases. The whole function here increases. So it is an increasing interval for the reciprocal function, right? Then we can sketch the left branch of this function like this, right? Okay, for the other branch, we can use a similar method to know that when x approaches positive infinity, the denominator should approach positive infinity, and the reciprocal should approach 0 from the positive side, right? And when x approaches 1 from the positive side, the denominator approaches 0 from the positive side. Then the reciprocal should approach positive infinity, right? So basically, the function here will have a pattern like this, right? And also note that when x increases, the denominator also increases, but its reciprocal, when x increases, the denominator also increases, but the reciprocal decreases, right? So the right branch is a decreasing interval. Understand? Okay, the other key points are the axis of symmetry x equals 1 is the vertical asymptote of fx. And y equals 0 is the horizontal asymptote of fx, right? And also we can calculate its y-intercept by letting x be 0, right? If x is 0, you can see that fx is 1. So the y-intercept is 0, 1. Okay, these are the key features of the function here. Okay, next, calculate, as you can see here, calculate the y-intercept of fx. We have already discussed this, right? Y-intercept is 0, 1. Next, label the y-intercept, local optimum, asymptotes, and any other key features of the graph of fx. So apparently there is no local optimum, nor any global optimum, right? There is only a asymptote here, which is x equals 1. Okay, step 5, remove any helping graphs if applicable. So what's left here is a graph of 1 over x minus 1 to the power of 2. Okay, do you have any questions to ask? Okay, if not, let's do a practice here. Sketch the graph of the function f(x) equals 1 over minus x squared minus 2x minus 1. Today's domain range x and y-intercept, asymptotes, axis of symmetry and behavior, local optimum, global optimum, increasing interval, decreasing interval, if any. Okay, I'll give you 5 minutes to think about this question. All right, have you finished? Okay, so we can start this problem by looking at the denominator first. First of all, we'll need to find the zeros of the denominator, right? So note here the minus x squared minus 2x minus 1 equals minus x plus 1 squared, right? So basically the zeros is x equals minus 1, right? So there is only one zero. And note that the leading coefficient is negative. So that means it opening down. And the only zero is x equals minus 1, right? Okay, so the axis of symmetry is x equals minus 1. So next, we need to analyze the left branch and the right branch. At the left branch, when x approaches negative infinity, when x approaches negative infinity, the denominator approaches negative infinity, right? And the reciprocal of a negative infinity should approach zero from the negative side, right? So that means when x approaches negative infinity, the reciprocal should approach zero from the negative side. So on this side, the fx should have a shape like this, right? And when x approaches -1 from the negative side, we know that the denominator approaches 0 from the negative side, right? For a number that approaches 0 from the negative side, we consider its reciprocal. The reciprocal should approach negative infinity, right? So on this side, fx should have a pattern like this, right? Okay, and as you can see here, as x increases in this interval, as x increases, the denominator increases, right? But the reciprocal decreases. So overall, as x increases, the fx should decrease. So this is a decreasing interval, right? So for the other branch, you can use similar method to analyze its end behavior and draw the curve in the other branch. Or you can just use a line of symmetry to directly draw the other branch like this, right? Okay, so basically the red curve here is the sketch of the fx. All right, so next let's calculate its x and y intercept. So when x is 0, fx is 1 over -1, which is -1, right? Okay, so now we know that when x is 0, so 0 is probably here. This is our y-axis, this is our x-axis. So note here, when x is 0, the denominator is also 0, right? The denominator is also -1, right? So the y-intercept is here. And there is no x-intercept. Okay, so let's make a summary of the key features. The domain is x belongs to real number, but not -1, right? Okay, range is from -infinity to 0, exclusive. X-intercept do not exist. Y-intercept is 0 minus 1, right? Asymptotes, vertical asymptote is x equals minus 1. And horizontal asymptote is y equals 0, right? Okay, and behavior, we have already analyzed and behavior, right? But you need to add up the and behavior on the right branch as well. So I'm not gonna write it here. You need to write this by yourself. Local optimum, there is no local optimum nor global optimum. Increasing interval. There is an increasing interval here from -1 to positive infinity, right? Decreasing interval. There is a decreasing interval from -infinity to -1, exclusive, right? Okay, please have a look at this question. Do you want to ask anything? Okay, if you do not have any questions, let's have a look at the third case. So this time, let's consider the reciprocal of a quadratic function where the quadratic function has no zeros. Okay, so for example, let's have a look at the function here. The denominator is x minus 1 squared plus 2, right? So apparently there is no zeros because x minus 1 to the power of 2 is always greater than or equal to 0, right? And then plus 2, it is always a positive number. So there is no zeros. So in this way, first of all, again, let's draw the graph of the denominator first. Okay, as you can see here, the leading coefficient is positive. So this function here opening up, right? And the vertex is the local minimum, which is 1, 0, 1, 2, right? And the axis of symmetry is x equals 1, right? So basically, this is a sketch of the denominator, right? And again, by analyzing its end behavior on the left branch and the right branch, you can find the graph of its reciprocal, right? So first of all, when x is less than 1, we can analyze like when x approaches negative infinity. As you can see here, when x approaches negative infinity, x minus 1 squared plus 2 should approach positive infinity, right? And the reciprocal of a positive infinity approaches 0 from the positive side, right? So this function should have a pattern like this when x approaches negative infinity, right? And when x is 1, we can just put x being 1 in the fx. We can get fx is actually 1 over 2, which is a point here, right? And we also know that in the interval from negative infinity to 1, as x increases, the denominator decreases, but the reciprocal of the denominator should increase, right? So overall, in the left branch, as x increases, fx increases. So basically, it will have a shape like this, right? And by using a similar technique, we can analyze that on the right branch, the function is decreasing from the local optimum here all the way down to approaching 0 from the positive side, right? So basically, the reciprocal of this quadratic function will have a shape shown in the blue curve here, right? And then we can find that the local minimum in the denominator here is actually a local maximum of the reciprocal, right? In other words, the vertex 1, 2 of the denominator, y equals x minus 1 to the power of 2 plus 1, corresponds to a local maximum, 1 over 2 of fx. Okay, next step, we can calculate the y-intercept of fx by letting x being 0. Then we can get that fx equals 1/3. So the y-intercept is 0, 1/3. Then we can label this y-intercept here, right? And then label y-intercept local optimum and any key features of the graph of fx. We have just calculated that the local maximum is 1/2, right? So let's label these 2 points here and then remove any help graph if applicable. So the blue curve shown here is the graph of fx. Do you understand? Okay, and the axis of symmetry is x being 1. Okay, any questions? No? Okay, if you don't have any questions, let's have a look at a practice. Sketch the graph of the function fx equals 2 over 2x squared plus 1, then plus 1. State its domain, range, x and y intercepts, asymptotes, axis of symmetry and behavior, local optimum, global optimum, increasing interval, decreasing interval, if any. Okay, I'll give you 5 minutes to think about this question. All right, any thoughts? Okay, so basically there are two routes by which you can get the graph of fx, right? For example, route 1. First of all, we can sketch the graph of the denominator 1 equals 2x squared plus 1, right? And then we draw the reciprocal of this function here. And then we enlarge the function. We stretch the previous function by a factor of 2 vertically, right? And then we can just translate the function in the previous step by a factor of by 1 unit up, right? And this is our final function here. So in this way, our steps should look like this. So first of all, as you can see here, when we draw 2x squared plus 1, this is a sketch of 2x squared plus 1, right? And then by analyzing its end behavior, we can draw the reciprocal of this function, which is shown in the dotted blue curve here, right? And then we vertically stretch the dotted blue graph by a factor of 2. So the vertex here is stretched here to 2, right? But the overall shape is similar to the dotted green line. Okay, next we translate the dotted blue line up by 1 unit, which will get you the solid green line here. This is actually the graph we are looking for, right? Okay, so this is our first method. The other route is you can also consider that fx is actually, if we divide both the numerator and denominator using a 2, it's actually 1 over x squared plus 1 over 2, and then plus 1, right? So we can first draw the graph of y equals x squared plus 1 over 2, right? And then find its reciprocal, which is 1 over x squared plus 1 over 2. And then just translate the function in the previous step up by 1 unit. This will give you the final sketch, right? Okay, so if we sketch x squared plus 1 over 2, it will look like this, right? The vertex is 0, 1 over 2. And then the reciprocal will look like this, right? And then, sorry, made a mistake here. Its reciprocal should look like this. So when x is 0, its reciprocal is 2, right? So the reciprocal would look like this. And then we need to translate the green solid line up by 1 unit. Then the final sketch should look like this. Understand? Okay, so let's have a look at this route. First of all, we draw x squared plus 1/2 like this, right? And after that, we draw the reciprocal of x squared plus 1/2, which is shown in the dotted blue line here. By analyzing the end behavior of the solid red line. So next, we can just translate the function of the dotted blue line up by 1 unit, which gives us the graph of fx, right? This is our fx. So you can choose either route to complete this task. Understand? All right, any questions? No? Okay, let's make a summary here. So today, we have learned the following key concepts. First of all, rational functions can be analyzed using key features, which includes asymptotes, intercepts, slope, domain, range, and positive and negative intervals, etc. Next, reciprocals of quadratic functions have different patterns depending on the number of roots of the quadratic functions. The behavior near the asymptotes is similar to that of reciprocals of linear functions. Last, all of the behavior listed above can be predicted by analyzing the roots of the quadratic relation in the denominator. Okay, so this is what we have learned for today. Okay, see you next time.